We can now look at maximum and minimum values of a function. There are what are called local maximum values, and there's what are called absolute maximum values, absolute min. Local, and this what I put up is called relative. So relative and local are meaning the same thing. So let's just read through this really quickly, and then we'll look at some examples. But we're doing similarly what we had just done before, looking at where a function is increasing and decreasing to find these values. So first we say that f of x has an absolute or a global maximum at x equals c if that value f of x is less than or equal to c for all x in the domain we're working on. Okay, so for instance, let's just look at that really quickly. Let's say we have some graph in here. Notice in here, I have multiple maximum values, right? So that's where we have a peak on our hill. So we have a maximum value here and we have a maximum value here. Those are what we would call both relative or local maximums, but there is one that is the biggest, right? So this one right here is going to be also called an absolute max. It's the biggest point that will ever be on that graph because I look at these arrows are going down. So it's never. If I was thinking about an absolute minimum though, because these are shooting downward forever, these are getting smaller and smaller. So there's no actually absolute minimum in here, but there is a local min because it's changing direction. And so this is actually considered to be a local minimum. I'm just used to calling it local, but again, some books call it different. So it could be called a relative. This would be a relative or local max. Later on, we're going to see that, hey, if we decide to close this interval where it's not going to be going on forever and ever, if I decide to close that interval, maybe this graph, like I said, isn't going on forever and ever, and we have some point where it stops, where maybe I have some, oops, let me rewrite it. If I did that, then I would actually have an absolute max and an absolute min in here, and it could occur on the endpoint. So notice that this point right here is the smallest point that happens on the graph. So if that was the case, we would call this the absolute min. So that's just kind of what's going on pictorially when we're looking at these. So let's just read through the rest. So we say that f of x has a relative or local maximum at x equals c if f of x is less than or equal to f of c for every x in some open interval x equals c, right? So I can basically put a little interval in here where this is going to be the maximum point in that little interval. Same thing, I can put a little interval in here, and this is the maximum point in that interval. So if I can do that, then those are also called local maxima or relative maximum. So similarly for minimum, so we say f of x has an absolute minimum at x equals c if f of x is greater than or equal to f of c for every x in the domain we are working on. And we say that it has a relative local minimum at x equals c if f of x is greater than or equal to f of c for every x in some open interval. So we can just close some interval around our max or min point. Okay, so how do we solve these? We can solve these finding local max and local mins, or maximum and minimums, by the first derivative test. So this says, let C be a critical number for a function f. So let C be a critical number for a function f. So recall, critical number, that was where our derivative was equal to 0 and where our derivative was undefined. We want to suppose that f is continuous on some open interval a, b, and differentiable on some interval a, b, except possibly c. And that c is the only critical number for f on AB. Let's see. Only critical number. On that interval AB. So one, we say that f of c is a relative or local. That's probably what I'm going to be calling it, local. Max maximum of f if the derivative f prime of x is positive on the interval AC and negative on the interval CB. Okay, and like is positive on AC and negative on the interval CB. Okay, that makes sense. Here's our A value. Here's our B value. We have some critical number that's falling in between, just one. And it tells me that my f prime, my derivative, is positive on AC, which means that it's increasing on AC. And then if it's decreasing, my derivative is negative on CB. That means it's decreasing. It's defined at this value. So if we have something that goes up and then comes down at changing directions at C, we can see that that has to be a max. So it's going to be opposite if it's a min. We say that f of c is a relative or local min of f if the derivative f prime of x is negative on AB or AC and positive on the interval CB. So if we look at the picture, it's negative on AC. So if it's negative here, it's going downwards on the left. And then it's positive on CB. So the derivative is going, it's positive. So our function is increasing. So if we have something that is dipping down, it's defined at C, and then dipping and changing direction and going up, going down, changing direction, going up. This value right here has to be a local min. So that's our first derivative test. So it's pretty much what we were just doing with finding where a function was increasing and decreasing. Now we're just going to add in that if it's defined at that value and it's changing direction, then it's either going to be a local max or a local min. So we're looking at the example, f of x is equal to x cubed plus 3x squared minus 24x plus 2. It's telling us to find all the x values of any relative extrema. When you see this word extrema, this is telling us we're trying to find a max or a min. Think of it, max is an extreme point, min would be an extreme point. So this is looking at any max or min. But when it says find the value of any relative extrema, the value is always the y value of your point. So this is the y value of the point. And you have to look at the original function. So we're going to look at where is this function increasing and decreasing. From there, we can see if it's going to be a max or a min at those values, and then we can plug it back into those x values into our original function to get the y value, which would be that value of the extrema. Okay, so taking the derivative of f of x, so f prime of x, using our power rule, derivative of x cubed is 3x squared, plus derivative of 3x squared, that would give us 6x. And the derivative of negative 24x is minus 24. And the derivative of 2 is 0. So we're looking at where is this equal to 0 and where is it undefined. This is defined everywhere, so we don't have to worry about that. So we want to look at when is f prime of x equal to 0. When I set this equal to 0, let's factor out a 3. There's a 3 in common with 3, 6, and 24. So let's pull out a 3. That would give us x squared plus 2x minus 8 equals 0. To me, it's just easier to factor if my coefficient in front of x squared is 1. I can do that. So that is factorable. I can see there's two numbers that multiply to negative 8 and would add to a positive 2. So we can factor that as x plus 4, x minus 2. So setting that whole thing equal to 0. 3 is never equal to 0. X plus 4 is equal to 0 when x is negative 4. And x minus 2 equals 0. Add 2 of both sides, we get x is 2. So these are our critical numbers. And we want to put those on our number line. And we want to test a value on each side of a critical number. So we have a critical number of negative 4 and we have a critical number of 2. So anything to the left of negative 4. So how about negative 5? Again, we're just worried about, is this positive or negative when we plug it back into the derivative? So f prime of -5. If we want to, we can think of this in factored form. So if we take 3 all times x plus 4, x minus 2. So if I plug in -5, 3 stays positive. -5 plus 4, that's a negative number. And -5 minus 2 is also a negative number. So if I'm multiplying a positive times a negative, I can see that that number is greater than 0. And so on the left of -4, that function is bigger than 0, the derivative, so it's going to be increasing. It's going upwards. So choose a number in between -4 and 2. If 0 ever falls in that interval, that's usually the easiest to choose. And I'm going to plug it back into this one, just because that's easier for me to see. If I plug in 0 wherever I see an x, I'm just going to get my constant, which is -24. So f prime of 0 is -24, which is a number that is less than 0. And so my function is decreasing here. So right now I can tell that x equals -4. The max occurs at x equals -4. That's not the maximum value, but that's where it occurs. We'll find the maximum value in a second. And now let's choose a number bigger than 2. So how about x equals 3? And if we plug that back into the derivative, so to me, the factored form would be faster to see if it's positive or negative. Well, 3 is always positive all times. Well, 3 plus 4, that's a positive number. And 3 minus 2 is also a positive number. So if we multiply 3 positive numbers together, the number is positive, it's greater than 0. That tells me my function is increasing after 2. So I can see here at x equals 2, we have a min at x equals, a min occurs. At x equals 2. Okay, so that's the location of our max and min, but to find the value of those, we have to go back in and we have to plug it into our original equation. Okay, so our original equation is this. So we want to look at f of, now we actually need to figure out what the number is, -4. So we're going to go in, plug in -4 wherever we see an x in our original. So I'm going to put parentheses in first wherever I see an x. So parentheses cubed plus 3 parentheses is squared minus 24 parentheses plus 2. Now going in and plugging in -4. So if I cube -4, -4 times -4 is 16. 16 times -4 is -64. -4 squared is 16. 16 times the 3 in front, that's going to be 48. Did I do that right? 16. Yeah. -4 times -24. So that's going to be positive. That's going to be 96 plus 2. Okay, so let's sum those up. -64 plus 48 plus 96 plus 2 gives us back 82. So max occurs at x equals -4, and the maximum value is 82. So if they had asked where the point occurs, the point on the graph, right, is x value is -4, y value is 82. And then last thing we want to look at, what is the y value when x is 2? So let's go in and plug in 2 wherever we see an x. So f of 2. So we're gonna 2 cubed plus 3 all times 2 squared minus 24 all times 2 plus 2. Well, if I cube 2, I get back 8. 2 squared is 4 times 3 is 12. Minus 24 times 2 is 48 plus 2. So 8 times 12, 20. 20 minus 48, that's -28. -28 plus 2 is -26. So our min value is -26. And if we wanted to look at that point there, that point, right, our x value is 2 and our y value is -26. So it's very similar to what we were just doing with finding where a function is increasing and decreasing. We're just now tacking on what's happening at that critical value. Is that going to be a max or a min? It's possible that it's neither. But we can tell if it's a max or a min if it's defined and our function is changing direction from increasing to decreasing or decreasing to increasing.